Okay, so let's talk about the carbon cycle again. The reason why we're doing this, even though there's some of this is repeats and maybe some of you already know this kind of stuff, and we've talked pretty extensively about a lot of these things. This is to remind you that the other half of the radiation budget equation is coming from the infrared terrestrial radiation side. So we've just spent a couple weeks talking about and thinking about the solar radiation management, basically blocking the sun, right? Using aerosols in the stratosphere. Now we're going to talk about the other side of the equation, which is dealing with the greenhouse effect, which is also, something that we can modify if we're trying to deal with climate change and deal with global warming. So on the solar radiation management side, basically we're just dealing with the input, the sun's radiation. Now we're ignoring for a moment the sun, and we're just talking about the greenhouse effect. So obviously, the number one thing that we can do for the greenhouse effect side of the equation is stop emitting greenhouse gases. Um, so we'll start there, right? We can also do that for dealing with all the issues of climate change, but specifically when we're talking about this carbon sequestration side of the equation, or geoengineering techniques, sorry, we're talking about dealing with the greenhouse effect. So let's pretend that we're not going to reduce emissions fast enough to avoid catastrophic climate change. Another option that's been proposed, and we'll talk about this extensively probably next week, is removing carbon from the atmosphere. So if we're not going to stop putting it there, some people propose that we could just remove it out of the atmosphere. And that's twofold, and there will be more details forthcoming. But before we get there, let's talk about the carbon budget. And I may go a little bit over today, but hopefully not too bad. So let me save this. Let me save this. And let me open here. All right. So the carbon cycle, okay, I think we've talked about it. I can't remember how much we've talked about it, to be honest with you, because this whole semester feels like a haze to me with everything going on. And I teach 3 classes, and I talk about this in all 3 classes. So if this is a redux, then lucky you get it twice. So why carbon? Carbon is an element in the periodic table right here, right? Has a elemental number of 6, has a atomic weight of 12, and it is considered to be the building block of all living things. And this is because carbon needs 4 electrons. So remember from chemistry, if you ever took a chemistry class in high school, or in college, we did just get a chemist at CIC, so that's fun. I hired her also. She's good if you ever get a chance to take her class. Or I helped hire her. So because carbon has an atomic number of 6, remember the levels of electron valences, right? So in the first level, there are 2 electrons, and in the second level, there can be up to 8, which means that a full completed atom really wants to have 2 or 10 electrons orbiting it. Carbon only has 6, so it has 4 empty electrons, 4 lonely electrons that are really good, very friendly, they're very sharing and gratuitous, they love everyone, and they want to bond with pretty much any atom that's nearby and willing to talk to them. They've had a long pandemic and they just want some interaction with other atoms. So they form bonds with other atoms in infinite structures, and therefore it is the core atom of the complex structures that create living things. It's in everything that's alive, and it's one of the most ubiquitous atoms on the planet. It's considered the building block of life, and scientists can't imagine life without carbon. So we do need carbon. So let's not villainize carbon. She didn't do anything wrong. and she deserves our love and respect. So, unfortunately, though, she is a major player in the greenhouse effect because there is a lot of carbon dioxide floating around in the atmosphere and methane. So to remind you of the greenhouse effect, this is the greenhouse effect. I know we talked about this, but we're going to talk about it again. So the atmosphere, okay, is full of gases, all kinds of gases. Does anybody know or want to volunteer what the most plentiful gas is actually in our atmosphere currently?
Nitrogen.
Nitrogen. Good, thank you. Do you know what percentage of all the atoms?
70%?
Yeah, it's about 70%. Good, cool. Thank you. So nitrogen is the most plentiful gas in our atmosphere, and it does nothing, basically. It's what we call inert. It's light passes through it, radiation passes through it. It's very, we don't see it, it's just there. We don't even really do anything with it. We breathe it in and we breathe it out. That's it. The only time that we see or have any indication that there is nitrogen in the atmosphere, there's one specific event. This is totally unrelated to the lecture, but I'm just curious if anybody knows the one time where we actually see or are reminded that there is nitrogen in the atmosphere. Does anybody know or want to guess? I'll give you a hint. It's more common in our summer.
Is it plants?
It's not plants, but that's a really good guess because plants do need lots of nitrogen. Oh man. Sorry. Yeah. Tito! Hang on. Sorry. Okay, so, oh my gosh. So the one time when we are reminded that there is nitrogen in the atmosphere is lightning. So lightning is actually, there's so much energy in the atmosphere that it rips apart nitrogen bonds. And the nitrogen bonds of the nitrogen in the atmosphere are so strong, that's why it's so inert, that's why it doesn't do anything. That they need a ton of energy to be ripped apart, and the only way they can get that energy is from the energy that produces lightning. So when you see lightning, the light, the crack, that's literally like you're seeing the atoms being ripped apart. So that's pretty cool. Okay, so nitrogen, oxygen is also very plentiful in our atmosphere. What's not very plentiful is actually the greenhouse gases, but they're very potent because they do one really important thing. And what they do is they are really, really, really good at absorbing infrared radiation. So infrared radiation, reminder, is the radiation that comes off of the surface of the Earth. So the surface of the Earth is a black body, it has a temperature, and it emits radiation. It's different radiation than radiation from the sun, because the Earth is a lot cooler than the sun. It emits radiation that's less energetic, and so that type of radiation is infrared radiation. So greenhouse gases, carbon dioxide, methane, and others, are not good at all, okay, at absorbing or interacting with the light from the sun. So here's, for example, look at this graph right here where my mouse is. This is the absorption percentage of carbon dioxide. So here is the sunlight, the incoming solar radiation. You can see here it's like this rainbow. You can see that CO2 is basically transparent to incoming solar radiation. There's no interaction. But these little black blobs here are the wavelengths of light that these gases absorb, that they intercept. So carbon dioxide doesn't intercept anything less than like 1.5 microns, which is infrared radiation. This is when we start to get into infrared radiation. So, but once we do get into infrared radiation, you can see that the combination of like carbon dioxide and water vapor, which is also a greenhouse gas, and others in the atmosphere are really good at absorbing the outgoing infrared radiation, except for this one sort of narrow band here where some of it gets through. Okay? Otherwise, they're really good at absorbing infrared radiation, carbon dioxide and greenhouse gases. And so when they absorb that infrared radiation, okay, they also assume a temperature and they send that radiation back down to the surface of the Earth. And this is what keeps us warm and habitable and a nice, pleasant place to live, is the greenhouse effect. So we need that carbon in the atmosphere. We do need it there. I don't want to get rid of all of it, just some of it. So we do need some of that carbon there. Okay, so then let's talk about the carbon cycle specifically. So that carbon in the atmosphere, it didn't just get there on its own. It got there from other places. It got there from plants. It got there from the ocean. It got there from rocks, all different ways, okay? Volcanoes, they explode and they put carbon in the atmosphere. And then that carbon in the atmosphere, assuming that there's no people, okay, for a second, there's no people on Earth doing any people things. There's just the Earth. So volcanoes, they emit this carbon, it goes up into the atmosphere, it's there, it's hanging out. Maybe now there's a tree, and trees, of course, they need carbon to grow, right? So the tree absorbs that carbon out of the atmosphere, and it grows. It grows leaves, it grows fruits, it grows plants, whatever. Okay, so now that carbon moved from the atmosphere to a tree. Let's say now the tree died. The tree dies. That carbon gets eaten up by little microbes and bacteria and bugs in the soil, and they poop it into the soil. And now that carbon went from the atmosphere to the leaf of a tree to the gut of a bacteria to the soil. Okay, now it's in the soil. Now let's say it rains. The rain wipes some of that soil away with the carbon in it, right? And that runs off into a lake, and then the lake runs into a river, and then the river runs into the ocean. That carbon is now in the ocean. Now that carbon is in the ocean, maybe in the ocean it gets taken up by an algae or a plant. Okay, it grows in the ocean into, like, let's say seaweed or something, and then that gets eaten by a fish. And then the fish dies. And then the fish dies and it takes that carbon with it and it sinks to the bottom of the ocean and it decays. And then over time, over a really long period of time, millions and millions of years, that carbon goes back into the rocks, right, as it's decaying. And then let's say in 1,000,000 years from now, another volcano erupts and it's that same carbon and the cycle continues. That is the carbon cycle. That's the carbon cycle without people. Carbon is moving between all of these things all of the time. So here is a vintage chart that I took from a really old scientific paper. I love how these things looked back then. So kind of like, I don't know, like this like computer like graphics are great. But it's basically just showing what I just described. You've got the atmosphere and all these arrows are the carbon that's moving between all the different parts of the Earth system. Here's a better image. So the current carbon cycle is different a little bit because of humans. So the major reservoirs where there's carbon are the atmosphere, the ocean, the plants, the soil, rocks, and then fossil fuels. Oops. And fossil fuels is an important part of this equation, right? Because everything I just described to you in the last slide, the difference between that slide and this slide, so everything I just described to you in the last slide can be represented by these green arrows. Okay, so you've got the atmosphere and like maybe the photosynthesis takes it out of the atmosphere and then the plants die and then the microbes eat it and that goes into the soil and then it washes into the ocean and then there it stays in the rocks until maybe another volcano erupts it again or something. It can also form fossil fuel deposits when it dies or when this organic carbon sinks down. And what happened is humans realized that this is really good at heating our homes and powering our machines and our cars and our factories. And so we're ripping this carbon out of the ground and we're putting it directly into the atmosphere. This is not a natural process. So here we have the natural carbon cycle, and now we have this unnatural process, right? We're back to that word natural, unnatural. This unnatural process of humans taking dead carbon out of the depths of the earth and putting it directly into the atmosphere very quickly. This wouldn't happen normally. This wouldn't happen unless we were doing it. So humans have altered the carbon cycle. And you can Google carbon cycle and you get all kinds of images like this where the natural carbon cycle is in one color and then the human components are in red. Right? Or in this case, it's like blue is the natural one, and then in this case, these over here are all the natural processes, and then this is the human influence, this corner. So we're not going to do that activity because I don't want to. But I am going to go to this image. So I like this image the best out of all of these. So here's where all the carbon is in these boxes. These boxes represent the different reservoirs, as we call them, of carbon. And the arrows are the carbon cycle. The red arrows are the human influences. So you'll notice there are quite a few red arrows on here, when actually the only thing that humans are doing deliberately is this one. We're taking carbon from fossil fuels and we're putting it directly into the atmosphere. That's what humans are doing. So then what's up with all these other red arrows? Well, these other red arrows are how the carbon cycle is responding to our idiocy. So humans are doing this, and the carbon cycle is like, whoa, 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 whoa. Hold on a second. We had this nice arrangement where I have this totally equilibrated, in equilibrium carbon cycle, and now you're dumping, in this case, if we average out from 1850 to now, that averages out to 16.4 gigatons of carbon every year that we're dumping directly into the atmosphere. This is an unnatural perturbation to the carbon cycle, and so the carbon cycle is like, all right, I'm going to do my best to adjust and make up for your folly. And for a while, maybe it was working a little bit, but now we're moving so much carbon from fossil fuels into the atmosphere that the carbon cycle cannot keep up. But what it has done is it has adjusted by adding, so if we take this 6.4 gigatons of carbon per year average since 1850, 2.6 gigatons of carbon every year is going into additional growth of forests. So the forests have expanded, actually, since 1850. Now, they're not expanding at the equator, because that's where we're chopping them down, which is also contributing to us putting more carbon into the atmosphere. But they are expanding in the northern hemisphere. So they're moving further north, towards the North Pole. And there are more and more forests every year. And those forests are coming up because trees love carbon dioxide. There's more carbon dioxide in the atmosphere. And they're like, hey, okay, fine, I'll grow. If you're giving me more carbon, I'll do it. Problem is they can't go fast enough to take all of it out. Another way that the carbon cycle has responded to us is the ocean. The ocean is also taking up more carbon, and it's taking up about 1.6 gigatons of carbon extra every year. And that's because the ocean, carbon dissolves easily in ocean water, and the ocean is not saturated with carbon currently. We'll know when it's saturated with carbon when it resembles seltzer water or soda water. Soda water also has carbon dioxide in it, but it has so much carbon dioxide in it that it has bubbles, and that's how it gets fizzy. And the bubbles are literally the carbon dioxide escaping. That's because there's a ton of carbon dioxide in soda water. There's not that much carbon dioxide in the ocean, but there is room for more. So both the land and the ocean combined are taking up, if I add these two numbers up, they're taking up about 3.2, a little bit more than that. Let's say 3.2 gigatons of carbon every year away from what we're emitting. So when we look at a graph, since the beginning of the Industrial Revolution, since 1850, you can see that the amount of carbon emissions that we've emitted every year in this black line doesn't match the concentration of carbon dioxide increases that we're actually observing in the atmosphere. So that's this dashed line. And that's because only about 45% of all of our emissions are staying in the atmosphere. The other 55% are going into the expansion of these forests and the additional uptake by the ocean. Okay. So of the amount that we're emitting every year, an important number to remember is only about 40 or 45% of it is staying actually in the atmosphere. The remainder is getting taken up by the ocean and by the land. And this is another way of looking at that. So if we look at the concentration of carbon dioxide in the atmosphere, we measure the concentration in ppms, which stands for parts per million. Parts per million. So for every 1 million molecules of air, in 1750, 280 of those molecules were carbon dioxide. Not very much. It's a small percentage, but it's an important percentage. Small but mighty. So if we were to estimate how much the concentration should go up just based on our own emissions, coal, oil, gas, cement, and land use change, then we should be at around 550 parts per million. But as of 2012, and this number, of course, is changing. This graph is old, and they haven't come out with a new one yet that I can find that I like as much as this one. But in 2012, the concentration was only 393 parts per million, when it should have been 550. And that's because the land and the ocean took some of it out. They compensated for us. So that the actual concentration only went up 113 parts per million instead of like 250 parts per million. Okay. Does that make sense to everybody? Does anyone have any questions so far? Okay, cool. So I do want to highlight or make note of the fact that we are probably not going to run out of fossil fuels. There is a lot of coal left in the ground. So we may run out of oil, we may run out, this is how much is left, right? And this is how much we've emitted. So this much is how much we've emitted, this box, in the 20th century. Maybe we're up to like here now. This is how much coal we have left. We have quite a bit of oil and gas and tar and shale and stuff, but there's just so much coal that we'll just never really, run out in a short enough time frame for us to, use that as the only way to end climate change. So we're not just gonna like run out of fossil fuels. I'm gonna skip this one, and I do want to just briefly talk about the Keeling curve. So the reason we know how much carbon dioxide is in the atmosphere is because we have been observing it at the top of Mauna Loa since 1958. So in 1958, David Keeling, a scientist at the Scripps at UCSD, Scripps Institute of Technology, went to the top of Mauna Loa and put a very simple gas analyzer to measure the concentration of carbon dioxide in the atmosphere. And after 4 years, he was able to say with confidence that the rate was going up. This is the website. His nephew runs it now or something. But you can go to this and It gives you like up to the minute, this is as of April 12th. Um, Here's the full record from 1958. So the first concentration that David Keeling measured was 315 parts per million. We're now up to about 419 parts per million. So very high. We've gone up significantly. Um, and you can narrow this down so you can look at just like the last year. Here's what the last year looks like. Here's what the last 2 years looks like. Okay. So something that's interesting about this curve is that even though it's going up, there's peaks and valleys every year. Does anyone want to wager a guess why the concentration of carbon dioxide peaks at the end of May and then reaches a low right at the beginning of October? And then the next year goes up a little bit more. Does anybody want to know why it's doing this particular behavior? If you zoom out too, you can see it in the full record. Every year it goes up and down, up and down, up and down. Why do you think? Oops.
Well, does it have to do with, usually it starts to get colder in October and then it gets really hot in May, but I'm just not really sure how those seasons really correlate to.
Does it have something to do with like plants?
Yeah, so both of you are collaborating on the right answer here. Both of you are moving in the right direction. What about plants?
Well, in like starting in like October and in the winter, like their leaves fall off.
Yep. And what's in the leaves?
Chlorophyll.
Which is made out of?
Funky plant stuff.
Carbon.
Okay, carbon, yeah.
Yeah, funky plant stuff, mostly carbon. And when those leaves fall off, where does that carbon go?
The dirt.
The dirt, correct. And then bacteria eat it and they poop it out and they fart it out, and some of it goes into the dirt more and some of it goes back into the atmosphere. So you're absolutely right. Yeah, both of you caught on to the season things really quick. So starting in October, those leaves made of funky plant stuff fall off the tree, and over the course of the winter, the bacteria decompose that carbon, and some of it makes it back to the atmosphere. And then, beginning in May, the leaves start to get their trees back. Yeah, the trees start to get their leaves back, and that carbon gets taken back out of the atmosphere and put into the trees. So this happens every year. Good job, guys. Really good. That's great. You're like the first class that got it without any prompting from me. Good job. But we'll notice that every year, right, the peak is just a little bit higher. And that's that additional, like in 2019, the peak was 415. In 2020, the peak was 417, right, or so. And in 2021, we're pretty close to the peak. It's almost May. So it could be something like 420, which would actually be a really big jump. And that's because the pandemic is ending and everyone is moving around again. So emissions went up more this year than they did last year, for example. But this additional little bit above last year's peak, that's our emissions. That's what's staying there. Awesome job. So here we are. So we're heading for a peak that's somewhere like 420, 419, 420. 420. So 420 please. So anyway, so that's the peaks and the valleys. All right. Let's go back to the PowerPoint. I think I'm at the end here. Why is there a peak in May? And here's what it looks like if we just like take a screenshot of the Earth. Blazing fossil fuels, yeah. I wish not, but here's what the plant life on Earth looks like in September and in May. So the green is obviously where there are like leaves. So you can see that in September there's a lot of leaves in the northern hemisphere, and in May there's not. Really, they start coming back around this time, right? So, but there's more in the southern hemisphere. The problem is that in the southern hemisphere, there's a lot of ocean, and so there's just not as much oscillation. So the signal globally is dominated by the northern hemisphere, by Russia, Siberia, Europe, Canada, and North America. All right, cool. So this is all background info, or this is all important information for you to have as we start thinking about carbon sequestration. So there's all this carbon in the atmosphere, okay? And this is contributing to the greenhouse effect, which is causing climate change. And so one proposal that has been floated for managing climate change as a geoengineering proposal is to physically remove carbon from the atmosphere. So this can be done in a number of ways, which we're going to talk about in detail over the next couple of days. But the most commonly floated way is by basically attaching suction cups, if you want to think of it like that, or attaching instruments and machinery to the exhaust of a power plant. So instead of the power plant sending the wasted coal emissions out into the atmosphere, it's instead going into a system where it's converting it to through all this process, which we're going to talk about because it's kind of complicated, and then sending it back into the ground, kind of where it came from. So that seems like a really expensive way of dealing with the problem instead of just not emitting carbon dioxide. And that's a conversation that I would love to have with you all kind of next week, or once we've gotten through some of these major geoengineering techniques. And I think that one thing that always sticks out to me that I want you to continue thinking about is like the easiest thing is that we just stop emitting carbon dioxide. But we're basically, by pursuing geoengineering, whether it be carbon sequestration, which we're going to talk about next week, or solar radiation management, we're basically conceding that we're too committed to fossil fuels that we can't give them up, that we'd rather spend exorbitant amounts of money doing other things rather than just giving up fossil fuels or figuring out how to, trying to buy time, exactly. Instead of just stopping it, right? We're like, no, well, we can't give it up. It's like we're addicted. I've heard the word addicted to fossil fuels. And so instead of dealing with the addiction, we're just trying to find other ways around it, right? And so that's what this carbon sequestration is going to be. So the last thing I want to say is that carbon sequestration is expensive, more expensive probably than solar radiation management. In my opinion, it's probably a little less risky. But we're going to talk about some of the downsides to all of these. Before we get to the end of this course, we're going to talk about like what are some of the bad things that could happen from all of these. And so the risks and the downsides of carbon sequestration are less than solar radiation management. That said, it's very prohibitively expensive to do on a very large scale, whereas it's also expensive to dump aerosols in the stratosphere, but relatively less expensive than carbon sequestration. But carbon sequestration is being pursued, actually. There are power plants that have been constructed with carbon capture and storage. CCS is the acronym. If you ever see that, carbon capture and storage is what it stands for. Again, we're going to talk about this all next week. I'm just kind of rambling now. But this is happening. It's being employed. And in fact, there are startups, who are starting to work with open air capture and storage, which is literally just big fans that you put on tops of mountains that are collecting air and taking the carbon dioxide out of the air. All of this seems like a ridiculous way to avoid having to change our lifestyle somehow, or to invest in alternative sources of energy. So that's where we are with that. Any other comments or thoughts or questions about any of the material that we covered today? Go ahead, Leroy.
I was just looking at the syllabus, and I was just wondering when, or if this is already posted somewhere, and if I didn't see it, but when I'm blanking, when the assignment for the final project is going to be announced, like what we need to do.
Yeah, so thanks for asking. Today or this week. So I like, we have about 1 month. We have 4 weeks left for the class, and so I like to make sure that the final is posted with like a month before the end of class, right? We have 4 weeks. Is that right? So what's today? The 14th. So 1, 2. We have 3 more classes, but we have like 4. It's like 4. I think 4 full weeks or something. Anyway, so right, because there's the what's it called?
Critique week. That's why I was wondering. That's why, yeah.
So there's critique week and then the end of class. So anyway, so I will post that, and then we'll, if you have questions or whatever, we can talk about it next week. Sound good? Any other questions, comments, thoughts? All right, then I will let you guys go. And make sure you take the quiz today, which summarizes like all the solar radiation management stuff and the reading and all that. And I will see you all next week. Bye.
Thank you.